Okay, good morning. We had started on magnetic circuits in the last class. So just to reiterate what we had seen in the last class with regard to magnetic circuits, I specified that the closed path followed by a magnetic field line. That is what is known as a magnetic circuit. This is known as the magnetic circuit. And we talked about MMF, magnetomotive force, as the root cause for producing magnetism in a complete magnetic system. Okay, so this is the root cause for producing flux or magnetism. Magnetic flux or magnetism. So the MMF is generally specified by number of turns through which the current is flowing multiplied by the current magnitude itself. So totally it is going to be having the total magnitude of the entire MMF is going to be N multiplied by ampere, or if I write about the unit, I should write this unit as ampere turns. But the turns do not have any dimension. That is the reason why we would generally specify MMF as ampere. The unit will be ampere. Although as the number of turns increase in a magnetic circuit, it is going to actually increase the strength of the magnetic flux that is being produced because of this MMF. So as the number of turns increase, specifically the magnetism is going to increase. That's what we were trying to say yesterday. And when we look at the MMF per unit length of the magnetic circuit, this is not the length of the wire, it is the length of the magnetic path. That is generally known as the magnetic field intensity. So, which we specify generally by H. The symbol H generally refers to magnetic field intensity, and the magnetic field intensity, the unit for this is going to be ampere turn per meter or ampere per meter to be specific. If we go with exactly the dimension, we have to write this as ampere per meter. Then we said that if this H is the cause, I'm going to have H as the cause, then B or the flux density is going to be the effect. So the flux density is generally specified by the flux per unit area. So if I am looking at the flux being produced in a material, that per unit area, so I'm going to specify this as Weber per meter square. That's what we called as the flux per unit area, which is Weber per meter square. That is going to be the unit, and this is also sometimes specified as Tesla. So always we call the magnetic field intensity or MMF as the cause, and the effect will be generally the flux density or the flux that is actually produced in a material. So if I give a specific amount of magnetic field intensity in maybe air and in iron, then what is the kind of flux density that is produced in air, or what is the kind of flux density that is produced in iron for the same amount of magnetic field intensity? If I try to look at the ratio of the flux density produced in air versus flux density produced in iron, that gives me, the ratio gives me something called relative permeability. So the relative permeability is the index of the magnetic property of a particular material as compared to air or vacuum or a non-magnetic material. How much it is going to really enhance the magnetic flux producing property. So this is generally known as relative permeability. We derived actually in yesterday's class the value of permeability of free space from the definition of ampere. The definition of ampere basically in SI unit says that if there are two conductors which are parallel to each other, which are placed in vacuum or free space, and if the force between them per unit length when they are 1 meter apart, if I look at what is the amount of force produced between them in unit length, per unit length, if let us say this length is also 1 meter, then within that length, whatever is the force experienced by the conductors between themselves, if that is 2 multiplied by 10 power minus 7 newtons, then we say that the current carried by each of these conductors will be 1 ampere. That's what, is the definition of ampere. Because of which we actually derived what is the H value when one of them is just carrying 1 ampere of current. And if we try to find out what is the H value that will correspond to the magnetic field line which is passing through 1 meter distance, and we call that as H equal to 1 by 2 pi. And then we said that the force will be equal to B because BIL, if I is 1 ampere in the other conductor, and per unit length, we said that that will be 2 multiplied by 10 power minus 7 newtons as per the definition of the ampere. So because of which we said, if I try to calculate what is B divided by H, which we specify as the permeability, and we were talking about the two conductors being placed in vacuum or air. So this is going to give us 4 pi multiplied by 10 power minus 7. This is what we said as the permeability of free space. And for this, we derived the unit as Weber per meter square divided by ampere per meter. This is what we wrote as the unit, from which we could say this will be Weber per ampere meter. Or the same thing we said as Henry, because Weber per ampere we called as the unit of inductance from the expression that L di by dt equal to N d phi by dt. So due to which we specified inductance as N multiplied by d phi by di, and N does not have any dimension. So we said this is Weber per ampere, which is actually the unit of inductance, which is Henry. So this is Henry per meter, or I should be able to write this as Hm power minus 1. This is going to be basically the unit of permeability. So this is what we spoke in the last class. And after that, what actually we were talking about was, if let us say I compare the permeability. So if I try to compare the permeability of iron with that of vacuum, that is, if let us say I have a magnetic field intensity of 1 ampere per meter, and I am trying to apply this to, let us say, a piece of iron. That is, let's say I have a piece of iron around which I have wound a winding, and I'm applying to this magnetic field intensity of 1 ampere per meter. And another case, I'm just having the same winding in air, and I'm trying to apply the same H of 1 ampere per meter. If I compare the two flux densities that are created, that is B of iron versus B in air, if I try to compare, that is what is the relative permeability. So relative permeability of iron could be as high as 4,000 to 5,000 times that of air. So I am going to generally see the flux density in iron almost 4,000 to 5,000 times as compared to what I see as flux density in air for the same amount of magnetic field intensity. Okay. Now from this, we can say in general, if I want a high concentration of magnetic flux, I should try to use materials which are having relative permeability which are quite high. And this is one reason why many of the electrical machines, rather all the electrical machines, generally are made up of iron or any other ferromagnetic material. Because whenever you talk about an electrical machine, you are converting generally, except for transformer, we generally convert electrical energy into mechanical energy. So what is done in this way is in motors. So when we convert electrical energy into mechanical energy, that is generally done in motors. Okay, and this is done through magnetic medium. So this magnetic medium essentially is allowing you to convert the electrical energy into mechanical energy, because whenever you are going to place a current carrying conductor placed in a magnetic field is going to experience a force. Right? If it is placed in a magnetic field, it is going to experience a force. So this experiences a force. So it experiences a force due to which eventually it has to start moving. So when it is moving, we say that the electrical energy is converted into mechanical energy. That's what we say. And for that, you need the magnetic field. If the magnetic field is not there, this conversion cannot take place. So you definitely need the magnetic medium in between. So this is essentially done in motors. Whereas if you look at generators, I'm going to have mechanical energy which is imparted to the conductor, the bouquet of conductors or a bunch of conductors. A mechanical energy is imparted to those bunch of conductors with the help of some turbine, maybe hydro turbine, maybe steam turbine. So one of them, or wind turbine, that is essentially going to make the conductors move in magnetic field. So that is going to move in magnetic field. And the movement is imported by the turbine, whatever we are talking about. Depending upon if it is a hydropower station, we are going to use basically hydro turbine. If we are looking at thermal power station, we are looking at steam turbine. Even in nuclear power station, it is going to be steam turbine. If it is wind energy conversion system, it is going to be wind turbine. So that is going to rotate the rotor. The rotor consists of the conductors, and the conductor is going to have now induced EMF, or you are going to produce electrical energy. So we call this action as the generator action. So whether it is motor or generator action, you will basically need magnetic field as the wire media, which allows the conversion of electrical energy into mechanical energy and vice versa. And that is the reason why all the electrical machines generally require magnetic field, and That's why they are generally made up of magnetic material. Some ferromagnetic material will always get into picture. That is one reason why if you try to make a transformer, make an electrical machine just out of wood or aluminium or just air core coil, then the size would increase enormously because the flux density itself can be only 1/4000th or 1/5000th of what is happening in a ferromagnetic material. So that is going to result in a huge size of this particular electrical machine. That is the reason why we always go in for ferromagnetic materials when we are constructing an electrical machine. Now, having said that, let's try to see how to do magnetic circuit calculations. How are we going to calculate for a given amount of MMF? How much is the flux produced? How are we going to calculate that? So let's say I am given a particular value of MMF. I want to calculate how much is the flux produced. So this is what we mean by magnetic circuit calculations. Okay. So let us say I have a ring made up of iron like this. Okay. And let's say it has a circular cross section. It is going to have a circular cross section. And let's say the area of cross section is A, some capital A. And let us say I'm going to wind some winding around this, something like this I'm going to wind. And let's say it has n number of turns. So it has n number of turns and I'm going to take it out this way, and this is current I that is going through this, and this is n number of turns. So I'm going to say that MMF in this particular case is Ni ampere turns. Okay. Now I'm going to look at the flux that is produced here, and the flux that is produced, because the current is coming out here, I should show this as dot and I should show this as cross. So again, like yesterday what I showed, if I try to hold my right hand, the fingers actually indicate the direction of current, whereas the thumb is going to indicate the direction of the magnetic field. So from that I should be able to say that the magnetic field line will be somewhat like this. So it is going to be clockwise. So I'm going to have the magnetic field lines going like this. So I'm taking only one line, which is actually along the mean circumference, and I call that line's length as L. So L is going to be the length of this magnetic circuit or magnetic path. So I can say that H in this particular case will be Ni divided by L. That is going to be H. Okay. Now, if I say that the total amount of magnetic field lines that are produced within this iron ring, that is probably phi. That is what is the flux in Weber. So I should be able to write this as B, whatever is the flux density, multiplied by the area of cross section of this ring. So that is going to be B times A. Okay. So I should be able to write this as H divided by B should be equal to 1 by mu, where mu is the permeability of this material. So I should say this is 1 divided by the permeability of the material. In which case I can write now this H as Ni divided by L. Right? And I can write this B as B phi divided by A. So I should have A here. So I should be able to write this as, this is what is 1 by mu according to what we defined. So I should be able to write this as Ni divided by phi. If I try to write it, that should be equal to L will go up. So L divided by mu A. So this is essentially the ratio of Ni, what is actually the ampere turns or MMF, and flux, which is actually the effect. So I should be able to write this as MMF divided by flux. So just like how in an electrical circuit, so if I try to look at an electrical circuit, I am going to have a voltage that is applied to an electrical circuit that results in current. And if it is a DC circuit, we say V divided by the resistance is equal to current. This is what we say in an electrical circuit. On the other hand, if I try to look at a magnetic circuit, I am going to have the root cause, which is MMF, that is producing flux. So in this particular case, we say MMF divided by flux, which is equal to L divided by mu A, which we call as reluctance. So the reluctance of a magnetic circuit is extremely similar to that of a resistance of a magnetic circuit. And this decides how much reluctance is offered by a magnetic material, that is going to decide how much is really the flux produced because of the MMF. So obviously the reluctance is going to be inversely proportional to the permeability of the material. So I can say this is extremely similar to when we write R equal to rho L by A, where we say rho is the resistivity of the material through which the current is flowing. The same way here I should be able to say mu is the permeability of the material through which the magnetic flux is passing. Okay, so this is the permeability of the material, which plays a very, very vital role in deciding how easily it will allow the magnetic flux lines to pass, or how hard it is for the magnetic flux lines to pass through a particular material. Okay, so if I actually compare, right? So if I try to compare an electrical circuit and magnetic circuit, if I try to compare the two, what are all the equivalent quantities in the two cases? If I try to find out how we can look at the equivalence of the two, so I should be able to say that in one case the cause is EMF or voltage, and the units are volts. Whereas here the cause is going to be MMF, which is actually the unit is going to be ampere, because I'm neglecting the number of turns here, because that is essentially dimensionally it is not going to have any unit. So that is the reason why, although I have to write MMF as ampere turns, I'm writing the unit as ampere. The second thing is the effect what I have. The effect in this case is flux, and we call that as the unit as Weber. I'm sorry, I'm writing here effect is current in electrical circuit. So effect is going to be current, and the units are ampere. Ampere is the unit. Whereas if I am looking at magnetic circuit, the effect is going to be flux, and the unit is Weber. And here, if I say that what is really preventing from more current being built up, that is essentially the impediment or whatever which is, not allowing enough current to be built up, that is resistance. So that is essentially measured in ohms. So this is going to be V divided by I. Whereas here I'm going to say the impediment is reluctance. And its unit, let's try to see, this is ampere per Weber. So I'm going to have ampere per Weber, right? We said actually Weber per ampere as Henry. So you can call reluctance as Henry power. Is it ampere per Weber? Yes, this is ampere per Weber. So this is going to be essentially the reluctance unit is ampere Weber power minus 1. And the same way ampere Weber power minus 1, we said again, recall L equal to N d phi by di. So this is going to be Weber per ampere. So Henry is Weber per ampere. So this is just the inverse of that. So I can call this as Henry power minus 1. That is also fine. That is also the unit of reluctance. Now, as far as magnetic field intensity is concerned, here where we say H, which is ampere per meter, length of the magnetic circuit, ampere per meter length of the magnetic circuit, there is no equivalent quantity here in terms of electric circuit. We really, although we talk about electric field and so on, but that is not really correct here because that is more into electrostatics than in actual current electricity. So I would not really buy into that here, definitely. Whereas I can have current density here, which is ampere per meter square. This is very clearly, you can't have more than a particular value of current in a particular material because that depends upon how many free electrons are there. Unless you increase the thickness of the conductor, you cannot pass more and more current through that conductor. It will eventually melt. You cannot really pass too much of current through a conductor. So current density is actually the property of a material. The same way here we can say flux density, which is normally indicated by B. Here current density very often is indicated by J. So EMF voltage generally it may be specified by V, and effect current generally is specified by I. Very often the symbols that are used, right? And resistance, of course, we use R. MMF, we generally use MMF itself very often. Flux is generally indicated by phi, and reluctance is actually indicated very often in many of the books as some special symbol of R, written in a somewhat, stylish fashion. And magnetic field intensity is specified by H, and flux density B is specified by B, and the unit is Weber per meter square. So these are equivalents in terms of electrical circuit and magnetic circuit, and magnetic circuit calculations can be done in the same way like what you do in an electrical circuit. Only thing, you might have to calculate the reluctance for each of the paths appropriately. One major difference between magnetic circuit and electrical circuit. One major difference is that you need continuous supply of voltage. So continuous supply of voltage is needed in an electrical circuit to maintain the current. Whereas once magnetism is established, any further current or further MMF you give in a magnetic circuit is only going to go towards heat dissipation. It's not going to increase the amount of magnetic field that is really produced in a particular magnetic circuit. So that is one of the major differences. So any once the field is established, once the magnetic field is established or flux is established in a magnetic circuit, any further supply of MMF only will result in heat dissipation. It is not going to really go towards increasing the magnetic field strength or magnetic field energy. So this will not cause any increase in magnetic field energy. Okay, so this is the major difference between an electrical circuit and a magnetic circuit. Okay, now if we look at how do we do the magnetic circuit calculations by drawing an equivalent electrical circuit. So if I am looking at a particular, magnetic circuit. So for example, let me again take the same iron ring. So I'm going to have an iron ring somewhat like this. Okay. And I'm going to have the number of turns wound like this. So I'm going to have maybe several turns wound around this iron ring. And I'm going to look at how much is, so let us say I connect this to a voltage source like this. Okay, so this is going to be V, maybe the resistance is some R. So a current that is flowing is I ampere and I'm going to have n number of turns. So I should say MMF in this particular case is going to be n times I. Okay. Now, the reluctance of the iron ring, I should be able to calculate as L divided by mu A. And what is L? If I know the radius, mean radius of this particular iron ring, okay, so I should be able to say L is equal to 2 pi R divided by mu. And mu is going to be mu naught multiplied by mu r, where mu r is the relative permeability of the material of the ring. So that is going to be mu r. Now area of cross section, depending upon what kind of the cross section it has. If it is going to have a cross section somewhat like this, and let's say inner radius is R1 and outer radius is R2, So I'm going to have R1, R2 minus R1 as the diameter of the cross section. So I should be able to calculate the area as pi by 4 R2 minus R1 the whole square. Pi r square. So I am essentially calculating it like this. So I can just write that as the area here. So this is going to give me reluctance. Now I should be able to calculate what is the flux value. So this can be shown somewhat like this. I can show as though I have a voltage source which is equivalent to the MMF. Okay. And I can look at the reluctance as though this is L by mu A, what I have calculated. And I'm going to say if I solve for what is the current in this particular equivalent circuit, that current is going to be same as flux. So this is a very, very simple magnetic circuit where I have just shown one particular material carrying the entire flux. And in fact, although I've shown this as though it is a little thinner, it is not thinner. So it is going to have the same cross section all over and it is a uniform ring. That's what I'm having. Okay. So in this particular case, I would say it is a very, very simple calculation. On the other hand, I can have magnetic circuits which are made up of two different materials, or there could be intervening air gap and things like that. So composite magnetic circuits, if I just see, which is made up of multiple materials or with different cross-sectional area and so on. So I can have maybe a ring like this, complete ring like this, and I am probably going to cut a small portion of the ring. So let's say I just, this is just erasing the whole thing. So let us say I'm going to have something like this. So I am cutting a small air gap in between. It is possible that I might like some particular piece to move here in some way or the other, depending upon the magnetic strength, magnetic field strength. This particular piece might move here and there. Okay. So this is a moving piece, whereas this is a fixed piece. So around this, I'm going to now wind my winding. So this is somewhat like this. So I'm going to have basically the wires wound around somewhat like this. Okay, so this is going to be the current that is flowing, whereas this is the number of turns. Now, clearly I'm going to have this particular portion. If I try to look at this particular portion, let's say this length is L1. Okay, whereas this length, this entire length, if I try to look at the complete circumference of this entire field, this is going to be capital or small L. Full length is L. So I should be able to calculate the reluctance. If I now try to draw the equivalent circuit, I should have the same MMF, which is N times I. But this is going to have two reluctances, one corresponding to the reluctance of the ring, which is L divided by mu of iron multiplied by area. And the second portion is corresponding to the air gap, where I have to write L divided by mu naught. And I don't know really whether all the lines are going to flow directly like this from here. If it is magnetic field line, whether all the lines will flow like this. If I assume they are all flowing directly, then it has to be L divided by mu naught A, and we'll have to close the circuit like this. Now I have to check What is the amount of flux that is flowing? So I would say this is essentially calculated as, if I may call this as reluctance 1 and I may call this as reluctance 2. So reluctance 2 is the reluctance offered by the air gap. Whereas reluctance 1 is reluctance offered by iron. So I have to say that in this particular case, the flux will be equal to MMF divided by R1 plus R2. This is going to be the flux. So whenever I'm going to have a magnetic circuit with different materials, whether they are connected in series, parallel, we'll have to look at it clearly and then say how exactly we are going to write this. See, for example, if I say that I'm going to have a magnetic material somewhat like this. So I'm going to have, let's say this is the middle portion of a transformer. And I'm going to have on one side like this, and let's say I have a small gap here, and then I'm going to again have a small gap on the other side as well, so I can have it somewhat like this. Okay, so again this is the kind of magnetic circuit I'm showing. So I will have, let's say I'm going to have some winding wound around here. And I am passing a current of I through this. Now this is a small gap G, and this is also a small gap G. Now what is going to happen is, whatever is the magnetic flux created here, it has to flow like this and finish its path. Similarly, this also has to flow like this and complete its path. So I am going to have this as though I am having an MMF here, which is common to both these limbs, and that is in the middle. And I'm going to have one reluctance on this side. So I can actually write the reluctance of this portion as this. So let me call this as some R1, and I can call this as R2. Okay. And I can call this as maybe again R2, because these two are very similar. And this is again R2. All of them are going to be actually R2. And I may have some reluctance for this limb also. Let me call that as R1. So I have called this as R1. Now R2 plus R2 plus RG. So I have to add 2R2 plus RG as the total reluctance of each of these parts. So I have to have this one and the second one. And I have to write 2R2 plus RG as the reluctance of this, and 2R2 plus RG as the reluctance of this. Please note that this flux is dividing itself into two halves, and half of it is going to go here and half of it is going to go here, because both of them offer equal amount of reluctance. So this will be roughly the magnetic circuit equivalence of this particular type of core. One thing I have to say is, because the permeability of iron is much higher, so this is going to be much higher than mu naught. I'm going to have mu I much higher than mu naught. So if that is going to be the case, if mu I is going to be much higher than mu naught, in that case, whatever lines that are flowing through this, they have to flow through this, all right, because it is a closed path. You can't have the magnetic field lines suddenly kind of, disappearing. You cannot make them discontinuous. So it has to flow through this. So when it is flowing through this, if I try to look at the flux density here, that is going to be some value which is corresponding to B ion. Whereas if I try to look at the flux density at this portion, which is air, that has to be much smaller, because if I try to look at what is B divided by mu naught, and the other case is going to be B divided by mu ion. So H is the same for both. So B obviously has to be much lower for the air gap. This will be lower. So if I call this as BG, BG will be lower, much lower compared to B ion. Okay? B ion will be much higher. So if all the lines flow through this, how are we going to account for the flux density somewhat being lower in the air gap as compared to what is there in ion? To take care of this, what happens normally is, if the air gap is big enough, if I'm going to have the magnetic field lines flowing like this, as it comes near the air gap, it is going to bulge. This is going to bulge so that the area of cross section becomes somewhat larger as far as the air gap is concerned. So this kind of bulging effect is known as fringing of magnetic field lines. So the magnetic field lines are going to kind of bulge, and then they are going to converge again once it comes back to the ion portion. So this is essentially the air gap portion where the field lines are going to bulge. So the flux density, which is actually flux divided by area. Here the area increases. Air gap area increases, whereas ion area is small, cross-sectional area is small. So which means I'm going to have B in air much lower than B in ion, which should be the case obviously if we are talking about the permeability having a ratio of 4,000 or 5,000. For the same kind of ampere turn what I am giving, the same amount of MMF that I am giving, I would definitely have less flux that is being created in the air gap as compared to what happens in the case of iron. So this essentially tells us that wherever we are going to have more air gap, if I'm going to have more the air gap, more MMF will be needed to establish the same amount of flux. Because obviously air is going to offer more reluctance. If it is offering more reluctance, obviously it is not going to allow more number of field lines or magnetic flux lines to flow through it. So if I want to force more and more flux lines to flow through it, then I have to give more and more forcing function, which is actually my MMF. The root cause has to be increased in its strength and intensity. So this is what happens in the case of, magnetic circuit wherever there is air gap. So if you look at a transformer versus a rotating machine, if I compare the two, I'm going to normally see that the transformers hardly have any air gap. Transformer is not going to have any air gap, because we might simply put, if this is the complete core of the transformer, there is nothing which is moving here. It's a static electrical machine, and we are just going to have maybe a primary winding here and a secondary winding here. I'm just showing a representation. This is not the way exactly the transformer is constructed, but I'm going to have the primary winding and secondary winding here. But the air gap is really not there, although there may, you can see there is some gap between these two. Generally, even this gap is minimized in a transformer. So you are going to see that air gap is hardly there. It's not going to be there at all. Whereas if it is a rotating machine, I necessarily need to have a gap between the stator and rotor. Otherwise, it is not going to be able to rotate. The rotor will not be able to rotate. So air gap is a must in between the stator and rotor. So obviously, rotating machines as a rule will require more amount of MMF. So these need more amount of MMF to establish a particular flux, whereas these need less MMF. That is sufficient enough because there is not going to be any air gap. Okay, so invariably you will see that the rotating machines, because if you look at a rotating machine, I am going to have probably a north pole here and a south pole here, and let me complete the stator arrangement. So this is going to be the complete stator arrangement. So we are seeing the stator, actually the cross section I am showing. So it is going to be a circular cross section, and this is what is the cross section of the stator. Now I'm going to have the rotor which is sitting in between these two. So I'm going to have the rotor. This is what is the rotor. And I'm going to insert the windings at the outer periphery. So this is how the windings are inserted. So if the rotor is rotating in whichever direction, let us say it is rotating in anti-clockwise direction, obviously you cannot have the rotor completely, plush with the stator and then still rotate. It will not be possible because there will be huge amount of friction between the stator and rotor, unless there is an air gap in between them. You are going to have the air gap in between them. So when you look at how the magnetic field lines flow here, I'm going to have the magnetic field line going like this and completing its path like this. And similarly, one more line, if I try to look at it, it may complete its path like this. From north to south, it will flow like this and then come back like this. This is how it is going to be. So you can see that there is definitely intervening air gap in between these two. Here is the intervening air gap. And we are going to have again intervening air gap here. So the intervening air gaps that are existing between the stator and rotor of a rotating machine is going to definitely demand more amount of MMF to be given to establish the same amount of flux. As in the case of a transformer, the MMF demand will be lower as compared to transformers demand. Electrical rotating machines will always require more amount of MMF because there is intervening air gap. Okay. Now, whatever is the line that is produced by the stator has to link with, or it has to have its influence on the rotor conductors also. Otherwise, it's not going to be useful for the electrical machines torque production or voltage production. If let us say there is a flux produced here, if it is simply coming around like this, and similarly it is a flux produced here and it is simply coming around like this. It's not even going and linking with the secondary. This is the secondary and this is the primary. In the primary, whatever flux is produced, it has to link with the secondary. Only then it is going to produce some useful effect. Otherwise, it's not going to produce any useful effect. So, what is not producing any useful effect, we call that as leakage flux. That is a useless or wastage. Whereas, what is linking with both from primary, whatever goes and links with the secondary. Similarly, whatever is produced in the secondary which is linking with the primary, that is generally known as useful flux, or you can say that is the mutual, because it is actually linking both. So we are going to have definitely some portion as leakage or useless flux and some portion as useful flux. How do we calculate these things? How do we do all the magnetic circuit calculations? We'll try to take a look at that in the next class.